Okay, I'm recording now. So I was saying that you have to calculate now the how many circuits do we need. So for we have a heating system. I'm going to go over this because the heating system probably we can't have a single phase circuit, and we will need a three phase. Let me find out today. But for the lights, we have this voltage, and depending on the power that we have here, so these are all the lights that we have in this building. Each classroom has 10 lamps, 50 watts each, and then the offices, the corridor, and the restrooms. So I told you that in this kind of public buildings, at least we have two circuits, one circuit for the first floor and the other one for the second floor. But you might have more. The more circuits, the better. So it's more complicated from the electrical point of view, but for us, it doesn't affect this complexity because we are talking about wires, and wires are very thin, and we can place the wires anywhere. So it's not like air ducts. Air ducts, you know, that are complicated to deal with, but with wires, this is something that this is a dialogue that we can have with our electrical engineer. Usually they tend to place a lot of circuits. This is good for electrical engineers. This is good for architects because we have everything in different sectors. Okay, so if there's an issue in the classrooms, okay, I have a circuit for the classroom. If there's an issue in the offices, I have another circuit for the offices. Then I can break it down into the first floor and the second floor. So the more control we have, the better. So why don't we do this? Because all these elements, the circuit breakers, wires, they are expensive. Okay, so the more circuits, the more expensive the installation will be. Is it relevant? It's not relevant to us, it's relevant to our client. So at least this is a dialogue, okay? So the more circuit breakers, the better. The more circuits, the better. The more wires, the better for electrical engineers and for architects. But that means that the owner has to pay more. But I think it's worth it because if there is an issue, we can identify easily where the issue is when we have a lot of circuits. If we have only one circuit for the first floor and there is a problem and we don't know where the problem is, we have to find out where this issue is. But if we have different circuits, we can try, okay, is the problem in this circuit? No, it's not. Okay, so the classrooms are working. Are the problem in the restroom circuit? Okay, yeah, this is because we have isolated different circuits. Anyway, you will deal with electrical engineers, you will deal with clients. When it comes to architecture, it's not relevant. We need to know that, and we need to know at least if we are opening this board, the electric board, we should understand what we are looking at. Okay, this is the circuit of lighting, first floor. That's fine. And this is the heating. Okay, so for the heating, I have this circuit breaker. So we need to understand what we are looking at. And then we have electronics. So the electronics, this is an educational building, so we can have computers, or we can have different plugs in the classroom or in the offices. So each classroom has this 400-watt power, and each office has this 200-watt. Again, how many classrooms? 3 classrooms times this is 1200 plus offices. At least we have to divide between electronics on the first floor and electronics on the second floor, at least. Okay, but we can have electronics, first floor, classrooms, electronics, first floor, offices, electronics, second floor, classrooms, electronics, second floor, offices, and so on and so forth. So this is what we have to calculate now. We have to divide this into circuits, and then we have to calculate the circuit breakers. The most important one, well, the most important, the most demanding will be this one, the heating or the cooling system. I can talk about heating or cooling. Well, another thing, if we don't specify anything, if we have this electrical system, we need another parameter to calculate this, is the power factor. So if we are not specifying anything, we can say that the power factor is 0.8. Okay, so this is a usual power factor. 0.9 is better. 1 is the best, but it's well, it's quite difficult. But everything that is above 0.8, it's acceptable. Okay, so we can say that the power factor is 0.8, and if we don't specify anything, the power factor is, we can take always 0.8. Okay, so now we have to deal with the heating or the cooling system. And to do this, we need first to work with this Excel file. Some of you have asked me things about this Excel file. I have sent you some tutorials, but I want to explain this for everybody because I think it's relevant. Okay, I'm going to do it again. And this is it. There you go. Okay, so this is the Excel file that you have, or you can download from the website. Here we have the indoor temperature, the relative humidity, outdoor temperature, outdoor relative humidity, indoor and outdoor enthalpies, number of people. With the number of people, we calculate the total CFM. And this is the specific volume, I think. No, this is, see, I think this is the specific pounds per hour. And then we have the ventilation load. Oh, this is this is not the specific volume. This is the CFM turned into pounds per hour because we need here BTU hours. Okay, and then we have the energy. So about the number of people, it's you have here, so each classroom has 20 plus whatever people times 20 CFM. So this is the total CFM of the classroom times 3. Well, times 6 because there are 6 classrooms, 3 on the first floor, 3 on the second floor. So we calculate the total number of people. You type this here, and then you end up having the first the load, the power, and then the energy. But if you read the statement, we need a heat recovery. The AHU, the air handling unit, has a heat recovery, a 50% efficiency heat recovery. So how can we do that in this Excel file? Okay, so here we don't have anything to include the energy efficiency of this heat recovery. So we are doing this without a heat recovery in our air handling unit. If we want to include efficiency, then we need to add 2 more columns to this Excel file. So let's do this. We can insert here a couple of columns. And here we can type efficiency. And efficiency, it's a percentage. Okay, so here we can type 50, 20, whatever. This is the air handling unit specifies this efficiency. It's not that simple. It's not that just 50 or 30. The efficiency of a heat recovery depends on the flow, depends on the outdoor and indoor conditions. But as average, we can say that the efficiency is 50%. Okay, and now here the final load. Once we have the ventilation load and the efficiency, here I need to specify the units, and units are BTU hour. Okay, so this is the ventilation load, this column, times the efficiency. The efficiency is 50%. Okay, so that equals this column here times this one, the efficiency, divided by 100, because this is 50%. So it's 50 divided by 100. and then we drag this down. There you go. Okay, so this is half this value. If we have a 50% efficiency, that means that we are spending half the energy that we have here. And now this energy, now it's connected to this column, but we have to connect this energy to the final load. So we have to drag this here. Okay, we click OK, and now we drag it, and there you go. So this is the final energy. It should be half the energy that we had without the 50% efficiency. Okay, but this is what is, so we have a heat recovery, a 50% heat recovery. So this is a way to save energy, on the heating or cooling systems, okay? So now the maximum ventilation load that we have is not in this column. It's in this column, but this is the thermal load. If we are dealing with the electrical systems, we have to turn this into electrical load. And how can we do that? With the COP. Okay, so we have a heat pump, an electric heat pump, and the COP, the coefficient of performance, is the it's the ratio between the thermal energy and the electrical energy. We have, you remember that we have two coefficients. We have the COP or we have the EER. With the COP, we have to divide watts between watts, or divided by watts. With the EER, we divide BTUs by watts. Okay, so since we have this COP and this is in BTU hours, we have to turn the maximum first. We have to take the maximum value of this column, okay, because this is the maximum. So what is the maximum? Is 176,535. Yeah, I think this one is the maximum. Okay, at this point, because this is the lowest temperature and the highest occupancy. Okay, so it depends on many factors. So the maximum power that we have is this. 176,535. So I can write it down. 176,535. BTU hour. This is the thermal load. I'm going to change the color. So the thermal load, the maximum thermal load is 176,535 BTU hours. Now we have to turn this into watts. So we can always find here BTU hour to watt converter. Watt to BTU, vice versa. So this is 176,535. Is this the, yeah, 176,535, and the watts are 51,737. 51,737 watts. Okay, so now what is the electrical load? The electrical load is the thermal load in watts, 51,737, divided by the COP, 3. Okay, so this electrical load is 51,737 divided by 3. It's 17,245 watts. Okay, so this is the electrical load that we have to deal with to calculate the circuit breaker. It's over 10,000. So in this case, we should be using a three-phase system. But imagine that our electrical engineer recommends single phase. Why would that be? I don't know. Doesn't make any sense. But just for the sake of the exercise, we're using a single phase thing. So what is the intensity? Intensity is the power divided by voltage times power factor. Okay, we have done this before. So what is the power? 17,245 divided by 240, because the voltage is 240, times 0.8. This is the power factor. And this is divided by 240 divided by 0.8. Okay, so this is 89.8 amperes. So do we have a commercial circuit breaker of 89 or 90? Probably not. So that's why I would say that we have to use a triple or a three-phase circuit. Phase. Okay. There is another formula. We haven't studied that formula. It's very simple. Well, it's very simple. It has a root square of 3 divided by, but it's just a formula. Okay, so to calculate the intensity in a three-phase circuit, there is another formula. Well, maybe I can place that formula somewhere. But this is what we have to do. If we find that we have a circuit breaker that it's not a commercial one, then we need to turn this circuit into a three-phase circuit because it will be safer, better, and yeah, it will be better. But I want you to focus on that. Okay, so we have the thermal load in BTU hours. So this is what we take from this Excel file. Okay, so we have to do this. Here we have to fill the indoor relative, the indoor temperature, indoor relative humidity, outdoor temperature, outdoor relative humidity, and the number of people. And then when we combine indoor conditions, outdoor conditions, and number of people, we have to select the highest number here in this column. Okay, so this is the maximum power that we are going to need. So we have to dimension our electrical circuit according to this maximum power. So we find where the maximum power is, and then we turn BTU hours into watts. Then we divide this electrical load by the COP. And then we apply this formula to calculate the intensity. We need to divide the power by the voltage and the power factor. And then we find this. If it's out of the commercial range, which is up to 40 or 45 amperes, I think, then that means that we need a three-phase circuit. Okay, so you have to do this with your numbers. So I mean, it won't be 36 and 156 because that depends on your ID. Okay, so do it. But now you know what to do. And then for the lights, this is up to you, but I want you to do it. So select how many circuits do you need, and then divide these circuits and calculate the power, and then calculate the intensity, and finally the commercial circuit breaker. And you have to do this with lights and electronics. Okay, so download this file again, this final assignment, because this last slide wasn't included. And remember that the power factor has to be always 0.8. If we don't say anything else, it has to be 0.8. Okay. If you want me to upload this, but I think you have to you should be able to do that with the Excel file. You should be able to include these two columns and to calculate this again. And if you have already done it, well, you only this graphic will be okay. So it changes, but it changes immediately. So you don't have to make this graphic again because it's linked to this one, to this column, even if you insert different columns here. Okay, so that's why Excel, it's wonderful. Okay. What else? Assignments. Final. Olivia, do you mind if we go over your assignment?
No, I don't mind.
Okay, so let's do it. Because you have already made all these calculations, and there are things that okay, so we have this heating power in winter and this heating power in summer. If you haven't done it, if you haven't included the 50% efficiency, so you have to divide this by 2, and that would be enough. Or if you want to do it again with a new Excel file, you can go ahead, but it should be half this value, okay? And what is the total energy in summer and winter BTU? What do you put here? You have to put this value, this BTU, okay? This total energy that you have here, okay? So this is the total daily energy in summer and winter. Well, and you have to do it twice, for summer and for winter. I think you have already done it. Yeah, if this is the winter, so this is the value that you have to put there, and this is the daily energy in summer. The only thing is that you have to divide this by 2 because it's a 50% efficiency. Then you have the graphic in winter, you have the graphic in summer. Okay, perfect. And now you are calculating the hot and cold water supply. You have calculated 16 toilets, that is 96 water supply fixture units. Okay, I'm opening. This is Noah's. Noah, are you there?
Yeah.
Okay, so this is your project, so I think it's quite good, so I will show it to the rest of the students. So you have done all this, so we have 4 fixture units. No, we are talking about water supply. Okay, so for the water supply, we have 6 fixture units of water supply. So let me find out. If we have 16 toilets times 6, it's 96. Yeah. And then 16, 6, 36 water supply fixture units. Okay, so that's correct. And then the total length, I don't know, I should be checking this. If this is the tank, the farthest one is this. So what is this length? This is 96. This is I don't see. Oh, 14. Okay, so you said that the maximum length it's around 140. Yeah, makes sense. And then you have to multiply this by 1.2, and this is the total length, 168. And make sure that you type the units. This is feet, okay? And the static head, 41 is the maximum developed length. If we look at the maximum developed length from this point to that point, is it 41? Yeah, because this is 15, this is 30. Yeah, so it's around, it can be 41. Okay. And then you have to multiply this times 0.433, and your maximum developed length is, no, your static head is 17.75. Okay, with the total fixture units, you have to add up these fixture units. It's 96 plus 36. It's 132. Okay, 132 water supply fixture unit. Then 168 feet. And I think this is Pascal, PSI. This is pound per square inch. A weird unit. Pound per square inch. Crazy imperial unit. So this is the pressure loss, or the pressure that you need to provide the heat pump, the water pump with. So with these three data, we can go to this table. So the first one, the maximum developed length, it's 168. So it's more than 150, so it has to be 200. So we are in this column. Then the supply pressure is 30 to 45. Yeah, so it's 30 to 45. It's for sure it's below 45 because it's 17. Okay, so we can take these values here, and then these values are the supply fixture units. So the supply fixture units is 132. So in this table we have 120. It's not enough. The following one is 175, and then we go here, and the minimum building supply in branch pipe is 2 inches. I can make it bigger. Okay, it's 2 inches. So yep, this is the minimum size, 2 inches. That means that if you are working with Revit, the minimum supply, this is 1/1/2. So then you have to change it because the minimum has to be 2 inches. You know what this means? So every single pipe that goes from, oh no, this is supplying to the air handling unit, sorry. This one is supplying to the, yeah. So this tank is going to the fixtures. So that means that when we are connecting all this together, as of this point, when we are connecting the second floor and the first floor together, so this is this diameter is 1/2, so it's even worse. So this has to be 2 inches. Okay, so everything that is connected to this has to be a 2-inch pipe all the way here. Okay, so this is what we have to check. We are doing this in Revit, that's fine, but then we need to check the calculations, and if the minimum branch from the supply until we start dividing the circuits, because here we have this branch going to the first floor, this one going to the second floor. So this, when we connect these two pipes, this has to be at least 2 inches, and it has to be 2 up to the tank. Okay, so that's the way we connect the calculations and the Revit file. Revit is wonderful because just modeling this with Revit, we can understand how many fixtures we have, and the distance, so we don't have to measure anything. So we only have to add all these segments up. But with Revit, we have this information. But then, according to our calculations, then we have to go back to Revit, and then I have to change this because this has to be at least 2 inches. So this is Revit. Revit doesn't calculate anything yet. It provides you with the values. Okay, so we have to calculate this because eventually there will be velocity somewhere, flow. Okay, so all these numbers, then we have to check these numbers. Okay, so by looking at this, at the flow, gallons per minute, we have the velocity, feet per minute. Okay, by looking at this, we can check if values are reasonable or not. Probably if we had this element, 1/2, that was what you had at the beginning. The velocity, yeah, the velocity is 29 feet per second. This is too much. Okay, so that's why it's a question of practice. I mean, when you have done this many times, you don't have to calculate anything. You just click here. What is the velocity? The velocity 25. Impossible. 2. Oh, that's fine. It's 2.6 feet per second. Okay, that's fine. But the first time you're doing this, you have to calculate it and then check. You have to check whether the velocity is reasonable or not. Okay. So Olivia and Noah, if you end up combining these calculations in your Revit file, you will have a nice, but now I need Noah's calculations and I need Olivia's and her group's Revit file. That's the idea. And the sanitary, we have the drainage fixture units, and then you have to create the 2 systems, the storm and the gray water and sanitary. I don't think you have done this yet, Noah. No, you have the sanitary system and you have a stack here for the gray water. I told you that you can move that stack, but anyway. But you have not included the storm. Okay, so I think if we are dividing this into 4 parts, that would be enough. Okay, so we have a shaft here, and then we have two shafts there. Yeah, I think if we divide this roof into 4 parts, we would need 4 different storm or rainwater stacks. And this is what you have to do now. We are here, and now we need to work with a horizontal pipe. How can we do that? Okay, so let's start with systems, pipe, and where am I? The elevation is 32. So I can start here. And then the diameter is not half. You have to calculate the storm stack diameters, can be 2 or 3. I think 3 would be enough, but anyway. And now I think we can go all this way. Oh, but we have to change the elevation because now it has to be on the basement. So the elevation here can be -2. Let's see what I've done. Okay, this one. Now I need to go up, draw pipe. I have to change the elevation, let's say 40. No. Draw pipe, change the elevation, it's 40 feet. There you go. Mierda. 40 feet. Look at this. And is it? Yeah. So we okay. So there's a this is a construction detail. I'm not talking about this because this is about construction, but we know that through this shaft there will be a pipe. This pipe will get all the water that rains in this part of the building, and then it will go down, and eventually we will get rid of it here. And now you have to connect this stack to this one, okay, because this is the gray water, and at the end we are collecting all the gray water here. And now we can copy this in different shafts. So there's another shaft here, and now we have to make sure that there is no intersection between these air ducts. Okay, so this is what matters now. And then there might be another one here, and we might need the last one here. Okay, and now from this point, we can draw a pipe like this, and then we have to connect it to this one, but with a 45-degree angle. There we go. Okay, so probably this is not the best way to do it, but the idea is that we have this pipe, so we want to get rid of the rainstorm water in the basement, and then there's another storm stack here, and then we need to draw a pipe well. Let's get to level 0. Yeah, there you go. Draw pipe 45 degrees. Well, we have to fix this, but the idea is that now we have to connect each branch. We have another one here, and then 45 degrees. Okay, so there's something, probably this element is not inserted. Okay, so you have to try to fix that, but we have to connect each vertical stack that comes from the roof to this horizontal branch, and then at the end we can mix this rainwater with this gray water that comes from the stack, because we need just there will be a tank here to get all this gray water and the rainwater, and maybe we can reuse this for watering plants or whatever. So at the end we end up having something quite complicated. Okay, because yeah, everything has to go. Okay, so at the end, we have a lot of pipes, we have a lot of ducts, and we have to make sure that there are no intersections. Are we done with this? No, not yet, because we have to insert something else. I told you that we need to duplicate the system. Why? Well, having a backup, it's always something good. If the main system it's having an issue, at least we make sure that we don't leave this building without heating or cooling, or without cold and hot water. That's why we have to supply water pumps. Okay, so always duplicate systems. It's good because in the event of an issue, we have a backup, and yeah, so the building is not out of operation. And this is the most important thing, especially if it's a business. So what is the backup plan here? So as you can see, we have these elements. We have these green rectangles here. And we have these green rectangles, and those are diffusers. So this is the split system. This is the indoor unit of a split system. So as you can see, in each office, we have this indoor unit, and then we have a duct with two diffusers. If we are working with a single family house, this is the indoor unit. So in single family houses, we don't need ducts because the rooms are quite small. But here in the public building, even this office, it's quite big. If we had only this element on the wall, well, it wouldn't be convenient, because you have to reach you have to reach every single corner of that room. So the air velocity, if we place this system in this wall, then we have to increase the velocity because we have to reach to every single corner. And this is not comfort. So that's why it's even better if we have an element here, and then we have a duct, and then we have two diffusers. So we distribute the air better with two diffusers than if we had only one. You can tell me, and why don't we have two diffusers here? I agree with you. So we should be having two diffusers, two air supply diffusers in this classroom, and two return diffusers, but we have only one. Well, because this building is not perfect. Okay, so it's just an example, but it can be better. So I think it would be even better if we had, instead of having a diffuser here, we can have two supply diffusers and then two return diffusers in this. You can do it if you want. But in this case, we have two diffusers. We have a split, and we have two diffusers. And then on the roof, we have these elements. Those are heat pumps. So as you can see, those heat pumps, we have 1, 2, 3 connections. So that means that this heat pump is feeding 1, 2, and 3 diffusers, most likely. Okay. And then we have another heat pump here and another heat pump there. So this heat pump probably is connected to this split system that we have here for this office, and this heat pump probably is connected to the classroom split units. Okay, so this is the outdoor unit, and this is the indoor unit. So this is the backup plan. If we have a heating and cooling system, we have a water heater, and we have a chiller, this chiller on the roof. Okay, the water heater is on the basement, the chiller is on the roof, and this is connected to the air handling unit. So the air handling unit is the ventilation system, and it is the heating and cooling system. What if something goes wrong? Well, we have the backup plan, because this is a heat pump. It can heat up and cool down the spaces. And okay, so if this system is not working, this heat pump with the split unit is working. And that it's not just because we can have issues, or it's because we have flexibility. Because if we want to imagine that we want to use this only for ventilation, we can, and this chiller and the water heater are not working. So we are ventilating with the air handling unit, we are supplying fresh air, and we are getting rid of exhaust air, so that's fine. And then we have this element to supply heat or cold. Why would I want to do that? Because maybe there are sometimes, because that depends on the efficiency. So this element has an efficiency, the water heater has another efficiency, and this heat pump has a different efficiency. So those efficiency depends on the indoor and outdoor conditions. So depending on if the system is smart enough, we can say, okay, so now we have the perfect conditions to supply fresh air, but I don't want this chiller to work, and I want this heat pump to work, because this is the optimum conditions for this system. Okay, now with other conditions, okay, so this is not the optimum condition for this heat pump, and the chiller is working better now. So I'm providing cool air with this chiller. So there are a lot of people involved here. We have the mechanical engineers, we have especially the software engineers. So we need sensors, and we need to analyze different indoor, outdoor conditions, occupancy, relative humidity, outdoor, indoor temperature. So depending on that, we have an algorithm, and then the system say, okay, stop the chiller, start operating this heat pump, and that happens. Okay, so this is out of our control, out of our, I mean, if we are architects, we are not dealing with these kind of things. But at least we need to know that we have a backup plan. So if this system is failing, we have another system that is providing the building with heat and cold, and we have flexibility. Okay, so by analyzing different parameters, we can operate this heat pump, or we can operate this chiller, or we can operate the water heater that we have in the basement. This is too complicated, and I don't expect you to elaborate or to design the algorithm to work with all these systems. That's why we have software engineers and electrical engineers and mechanical engineers. But at least we need to be able to talk to those engineers, because what matters from the architectural point of view are the diffusers, the ducts. Okay, so we can rely on those engineers if they think that having this system is better. Okay, we can agree, but then we need to know what it takes from the architectural point of view, having two different systems or three different systems in a building. Okay. Well, I have said that speech, but what do we have to do now? We have to try to do this. So Noah, you are done with well, the only thing that it's left, that you have to connect the chiller to the air handling unit. I told you how to do that. But now we need the backup plan. And what is the backup plan? We need split units. We need heat pumps on the roof and split units in each office. How can we do that? We have to insert a different element. I think Chris, is the final exam our final, or is there also yeah, there is also a final exam. I will talk about the final exam later, but yes, Chris, it's not that easy. So you have to submit the final assignment, and then we have final exam. But I will talk about this later. Now I want to insert two different elements that they are not included here. I think on my systems, mechanical equipment, boiler heater. Okay, so we do have a heat pump for split systems. I think it's included in the file that I uploaded on Canvas. Anyway, if you don't find this heat pump for split systems, you can insert, load family, and you have to go to mechanical, MEP, general components, heat pumps, and here you have the heat pump for a split system. It's a very basic one, but I think it works for this building. That one works. Okay, so we have to insert this heat pump for a split system. What we don't have is, so here we have to insert the system, mechanical, heat pump, let's say 3.5 tons. And we have to insert here on the roof, level 30. Okay, so this one is on the roof. Let's place it here. So this is the outdoor unit. Then we need an indoor unit, and split indoor units, I haven't found it here. So it should be in airside components, terminal units, and there are a lot of things for terminal units, but we don't have a split, an indoor split unit. So I have found this in, this is the air conditioner split system. I have found this in commercial websites. Okay, so if you, what are commercial websites? What is the, what do you think is the, do you know any brand that commercializes heat pumps or these kind of things? I'm asking.
No.
No. So if you, but you, I'm sure that you know brands for cars, and you don't know any brands for air conditioning systems.
Doesn't Mitsubishi do it?
Okay, Mitsubishi. Mitsubishi, something now, Mitsubishi. Yep, well, Mitsubishi is doing everything that we have to do. Mitsubishi Electric, I think. Yep, so with Mitsubishi Electric, Spain, but I'm sure that there's a Mitsubishi Electric, let's say, yeah, United States. Yes, they do, and they are quite good, and they are manufacturing this kind of, well, there are a lot of things you can do. So they have heat pumps, they have electric indoor and outdoor units, they have diffusers. Okay, so Mitsubishi, it's a good brand. The most, well, when I was a student, everything was about Daikin. Daikin. Daikin is the German brand, innovation technology. Now everything is about sustainability. Okay, so even oil companies, they are the most sustainable in the, so we have to be careful about that. Anyway, Daikin, yeah, so we have residential, we have commercial or public buildings. So it's a huge company, and they are reliable. And finally, we have Daikin, we have Mitsubishi. There are a lot of companies. So if we look at LG, HVAC. Okay, so this is LG. And I'm sure we have other companies. Most of them are from, I don't know any American brands for this. I don't mean that they don't exist, but I think people from Japan and Daikin from Germany, well, we have Carrier, HVAC. Carrier are, they are French, but if you, everything is sustainable, everything is green, everybody's happy using these kind of things, but this is advertisement, so don't believe everything you see on ads. Anyway, I downloaded these elements from one commercial brand, but I don't remember which brand was it. I don't remember. But I'm sure that if you type here in every single brand, if you type Revit files, well, they don't have a result for Revit files, but I'm sure that you can find families, Revit families from these brands, and they are for free. You only have to register your name as an architect or whatever, and then you can start downloading Revit products or Revit files. Okay, so all good companies, they have these kind of elements. So this is what I have done. And what do we have to do now? So once you have, well, I have downloaded many split systems. I want you just to use one of them. So you can drag it here. Okay, and then you can place it. So let's place it. This is a split system indoor unit. Okay, that's fine. And let's place it, let's say here. And now where the hell are we? Okay, so it can be on the roof. So we have to move it down because it has to be underneath this the structural slab here. Okay, so as you can see, we have a lot of pipes and we have a lot of ducts. So let me find out what we have here. On this top element, okay, so we have out. That's good because from this I can draw a duct. There you go. We can move it here. Okay, so I can have a duct from here. And then if you can see, we have inlet and outlet, and this is a fluid. This is not water, this is a refrigerant. Okay, so, and now we have to connect this to the heat pump. In the heat pump, we have inlet and outlet. So what would I do? I am working with the inlet here, so I have to connect this to the outlet. So let's draw pipe. And we have a shaft now, and then we have to move this to the shaft. Then I can change the elevation. If this is -2, I can work with, let's say, 2. And then from this one, I need to work with the outlet. So this is the outlet. And then I have to connect both. There you go. Okay, so I have connected this inlet to this outlet, and then now I have to connect the outlet to this inlet. Okay. Yeah. Okay, this is it. And as you can see here on this, we have this indoor unit, and then we have 2 diffusers. So I think it's always better if we work with a round duct. Okay, this is round, and it doesn't have to be, what is diameter? 26. It's too much. It can be 8, 10. Okay, there you go. And now this is only supply. We don't have return, because this is just this is heating up or cooling down the air, and it's supplying. So the return, I'll explain the return later. And now we need to copy two supply diffusers. This is supply air. So I can copy this here, and then I can copy this there. And now I can connect okay. Flex duct. Okay, there you go. And now with this one, can I do it? Flex duct. Okay, works. Okay, so this is the last thing we needed. We have a heat pump here, and we are connecting this heat pump to this. I will work with this again. So this is the outlet now. Go pipe. I can go this way, that way, and I can change the elevation to. And I can go this way now, and then from this one, vaya. Joder. I'm sorry. I there you go. Okay, if we are connecting things, there is always two pipes, inlet to outlet and outlet to inlet. And that's it. In this place, or in this drawing, what we have, you see that we have like 1, 2, 3 different heat pumps. Okay, so they are all connected to each other, but it's like having 1, 2, and 3 different ones, and each one is connected to 1, 2, and 3 different systems. So in this case, what I would do, if you had all these, okay, so we can have this for the first office, this for the second office, and this is for the third office. It's nice. isn't it? Okay, so with this, we are done. I mean, if you're able to do this, you are above the average. I mean, I don't think there are architectural students that can do this at the junior year, because this is high level Revit, and we are not talking about modeling. We are talking about understanding the systems. Okay, so we are dealing with systems. So it's not about Revit skills in modeling. That's another story. But having this knowledge or these skills about the mechanical and the plumbing template in Revit, I think it's quite good for an architecture junior year. Okay, so go ahead. Some of you, Mackenzie, are you there? No, she's not. Well, someone told me that there are issues with Revit in the computer lab. Is that true?
Yeah, I had some issues too.
There's like a licensing thing that comes up. Like I'm on the off-campus access, and there's like a licensing thing that comes up that you have to fill out. I can send you a screenshot of what it looks like if you want.
Well, I don't know. If you have issues working with Revit, I can talk to the IT, but there's nothing I can do because it depends on them. But I need to know if you have issues working with Revit or not. If you have Revit on your computer, your laptop, or whatever, go ahead. If you need to access the computer lab and you cannot do it, I need to see if it's just if it's something that will be solved tomorrow or after the break. I don't know, but I need to find out. So just let me know. If you can work with Revit, go ahead. If you can't, and if there's an issue that we can't fix until next semester, no problem, because I have a backup plan. So I always have a backup plan. So this is what you should do. So Noah, now if you can complete this, the rainwater stacks, and then you have to connect the rainwater stacks with this vertical gray water stack, and then to get rid of it in this part of the building. And then you have to insert these three heat pumps. Well, 3 heat pumps, and we have more here. We have one. Okay, so there are more. There are 3 more here. So probably these 3 heat pumps are connected to these 3 indoor units. And then there are another one there. And this one will be connected to probably this one. Okay, so here we have this, and we have 1, 2, 3, 4, 5 diffusers. Anyway, if you are working with this Revit file, go ahead. But this is what it has to look like at the end. So it looks like a mess, but it's not a mess. I mean, and I think it's interesting if you can work with colors. I think it would be great, because with colors everything seems clearer. Okay, so we have the gray for the exhaust from the toilets or the restrooms, and then we have the blue for the red for the supply and the blue for the return. So try to work with colors because it looks better. What is the backup plan? Okay, so if you are not able to work with Revit, we can always use Excel. This. Okay, so this is what I have done. I have this pink color is the supply diffusers. So you see that we have supply diffusers in the classroom, and we have supply diffusers in the office. So classroom, office, classroom, office, classroom, and office. And then here we have another branch with 1, 2, 3 supplies diffuser for this big office. Okay, so it's a long one. So one supply diffuser wouldn't be enough. So we have 3, 1, 2, and 3. Okay, so I have tried to do the same thing with Excel. This is just painting cells. Okay, so it's nothing. But we had classroom, 3 classrooms, 3 offices, 1, 2, 3 offices. And here, this is the vertical duct here. And here we have 3 different diffusers for the same office, but they are 3 different diffusers. So what do we have to do here? With Revit, we can work with the 3D model, and we can make calculations at the same time. Okay, so we're dealing with the Revit file. If everything is right, if I click here, I haven't checked that, but we have 0 flow. So that means that there's a mistake somewhere. But if it weren't a mistake, yeah. So here in this first floor, apparently is working well. So this is 1560 CFM, because you are adding up the heat flow that we have here. Okay, so there has been something wrong, because if we click here, so with this connection, there's something wrong, because probably you have a branch here that is not connected to anything. You have to close this branch without the diffusers, and then it will work. Okay, so I think this is the issue. Anyway, if we click here, we should be able to have the total airflow, and now we don't have it. But if we click here, we have all this information. We have the velocity, we have the flow, and we have the area, and we have this the diameter is 20. Okay, so the diameter is 20. The flow is 1040 CFM. The velocity is 476 feet per minute. And now we have to check. And what do we have to check? These are, so if you remember this table, these are branch ducts, okay, because they are in contact with rooms. We have main ducts for the one that it's coming out of the air handling unit, and the main branch duct can be the vertical one. Okay, but if we are inside the room and those elements are, well, they are inside the corridor, but I would say that those are branch ducts. Okay, so the speed or the velocity here should be from 200 to 600. That makes sense. So if we click this, the velocity here is 400, so it's perfect. Okay, so what is the velocity here? It's 700. So this is a little, this is probably too much, but well, the maximum should be around 600, and it's 700. It's not a big issue, but if you can make this duct instead of 20, it can be 22. Yeah, now it's 590, which is just 590. It's within the limit. Okay. So we can do this easily with Revit, but we can do the same with this Excel file. So this is what I want to show you. So here we have to type the airflow. So if this classroom has 25 people, 25 times 20 is 500. So this is 500 CFM. In this classroom, we have 3 classrooms, and each classroom is 500. Now this flow here, it's 4 people times 20, so this is 80. So we have 4 people, 4 and 4, so this is 80, 80, and 80. Okay, so those are the diffusers, the classroom, and the office space. And this, every time we add a diffuser, we have to change the conditions because the airflow changes. Okay, so from this diffuser up to this T, we have 500 CFM. And now what is the velocity? It's 91,000 feet per minute. It's too much. Why? Because the diameter is 1 inch. So what would be the right diameter? Let's say 8 inches. Now the velocity is 1,400. It's too much. Let's say 12. Let's say 14. Okay, with 14, we are within that limit because the limit has to be between 200 and 590. Okay, so now it's 460. That's fine. But now we are adding this. So at least if we are going in this direction, and this duct is 14, at least this has to be 14. So we cannot go, so the minimum is 14, at least all of them have to be 14. Okay, and now we have to check the velocity. So if this is 14 and this is 14, the velocity here is 460, the velocity here is 542. Is it acceptable? Yeah, because it's less than 600. Okay, so that goes well. I don't have to change the diameter here, so it's always 14. What about here? Here we are adding 500 CFM, and the velocity here is 1,000. No, it doesn't work. So let's make it 18. Okay, if we make it 18, this is 600. I think 20 would be better. Yeah, 20 it's better because now here we have 495. But if this is 20, now the rest of diameters have to be at least 20. Okay, so with 20 here, this is 531. That's acceptable. But now if we are adding 500 more, this is 760 with 20. So let's say 24. Okay, with 24, we are good. And this is 24. And at least this one should be 24 because this is the vertical one. Okay. Well, so you can do the same with this Excel file. Okay, you can draw the layout, and then you can add the heat flow that you have in each room here, and the heat flow that you have in each office space. And this is a very simple, what is this? So this is the CFM. So if we click here, the orange cells are the cells that you have to type or you have to change. Okay. And what about this one? This is just D8. So it's this. Okay. So the flow here is the same as in the diffuser. And then this is the velocity. You remember that formula, 144 times the CFM divided by the area. And what is the area? The area is a circle. This is for circular ducts. So if we have a 14-inch diameter, the area is pi times the radius to the power of 2. Okay, so this is the area of a circle. If this is diameter, the radius is half, and this is pi, the radius to the power of 2. And that's it. So what about this one? In this case, the flow is this diffuser plus this diffuser. And this is the same. So this is the CFM divided by the area, this velocity. And the area is this. So if you just copy and paste this elements. I mean, you can draw another layout. So imagine that you have okay, so you have layouts like this. Now what do we have to do? We can insert this. Here. So with this, we can type if this CFM is 400, okay, if this CFM is 100, okay, this is 200, and this is 300. So it depends on the occupancy, the CFM that we have on all these diffusers. And now we can start copying this table here. So what is this airflow? It's this cell. Okay, so this is 400. With this, you can, by changing this, if it's 12, okay, so this can be 12 because the velocity it's below 500. That's fine. What is the next branch? The next branch is this diffuser plus this diffuser here. And now the speed is too much, so we can make it 14. Okay, so now it's below this. Now we have a new branch here. So this is first one plus second one plus the third one. Okay, so this is the CFM, this is 600, it's too much. This can be 16. And now there's another diffuser here. So in this branch, this is this one plus this one plus this one plus that one. Okay, so now 16 is not enough because the velocity here is 700. So let's make it 20. Okay, so now it's, you see. So with you can prepare your own layout of supply diffusers. You can have one layout for supply, a different layout for return. And just by copying and pasting this table, the only thing you have to make sure that the airflow is, if here we have two diffusers, this airflow is the first plus the second. If this is the first, the second, and the third, that one should be the first, second, third, and fourth. Okay, so when we are adding more diffusers, we are adding different tables because every time we add a diffuser, we have to change the CFM. And that's it. Okay, so even if you can't work with Revit, let me know because I can send you different examples, and then you can work with this Excel file. You can draw your layout, and then, but this is what Revit does. I mean, in Revit is great because we are modeling, and we can find out if we have conflicts between ducts, pipes. But if when it comes to calculating the air ducts, this is a good tool, and we only need to work with the layout that we have in our building, and then copying and pasting these tables, we can calculate the diameter that we need to keep this velocity between 200 and 590. Okay, so even if you can't use Revit, let me know, because I can email you this Excel file. I can email you different examples with different layouts, and then you can calculate the air ducts with this Excel file.